So this is another one of these coupling in practice talks. This time it's about ice sheets, so ice based on land, running in a global climate model. I'm going to try and run through some of what we do and why we do it like that. So not just how the fields are passed, but what has to happen before the models can carry on running again. It's a pretty complicated set of stuff, and 15 minutes isn't very long to do all of this, so I will do my best with it. I sit halfway between kind of pure climate scientists, and I'm not really a proper technical computational person either. And I've been sat here watching all your very sophisticated technical coupling systems for the rest of the week going, you're going to think this is a bit crude. But I'll try and explain why we've done it this way, and what motivated us to approach it like this, and also some of the advantages of the way that we've done it. I think you'll be able to see what the disadvantages are fairly simply. So for people who don't know, the UKESM is the Earth System Model configuration of the UK Met Office HADGEM climate model. So that mostly uses OASIS as the coupler between the atmosphere and the ocean. We don't use that, and I will explain why. So this is just a quick introduction from kind of the science side of things, of why you'd want ice sheets in Earth System models. Because this is a relatively new thing for CMIP class, big kind of HPC climate models. So coupling ice in global models is not necessarily the best way to either do climate physics or ice physics. So I've got my two little sad faces up here. Climate modelers don't really want to do it, and ice modelers don't really want to do it either, if all you care about is the ice physics and dynamics or global climate. But there are lots of ice retreat processes that have big feedbacks with climate forcing in them. Difficult to run just kind of standalone ice sheet models too far into the future, because you just run out of sensible boundary conditions, because your climate model isn't, your climate forcing isn't changing with that. It's also really difficult to do sea level rise projections that are consistent with the kind of CO6 climate change stuff and all the stuff that the IPCC reports are based on, because you don't have this consistent system between the climate and the ice sheets running in it. And the further you get into the future, the more important ice sheet loss is for sea level rise. So I've got a bunch of bullet points up here about some of the reasons why it's difficult. There are massive disparities between the time and the space scales of the climate and the ice physics, as climate models and ice sheet models like to represent those physics. And there's a whole bunch of structural problems in the model codes themselves, because they're simply not, climate models just aren't written to have their solid boundaries move around and have all the other fields follow that. So really, I'm trying to make the case for why ice sheet coupling is not really the usual kind of coupled climate model thing that we do, and why maybe you wouldn't automatically end up using something like OASIS or a normal climate model coupler to pass fields and run the model like that. And that's, I mean, we started doing this in UKESM with OASIS, and we fairly quickly, for all sorts of reasons, ended up not using OASIS just for the ice bits. So I said this is a new kind of area of science, and different groups around the world who are doing it are working out different ways of doing both the science and the technical side of it, and working out what's scientifically effective as we go. There's been a few model talks earlier in the week that have mentioned PISM or other ice sheets kind of in the ESM systems as part of the coupler. Mostly, I think entirely, those are models of Greenland. So you can do the Greenland ice sheet basically just staying within the land surface and coupling with the atmosphere, coupling between the atmosphere, land surface, and the ice sheet model. And you can largely ignore what the ocean's doing. Once you bring Antarctica in, which is where some of the really big sea level things come in, and sea level is the motivation for doing this, that gets a whole bunch more complicated, because now you've really got to start moving where the ocean domain is as well. So we can do both of those things in UKESM ice, and I shall go on to talk about that. All right. So on Monday there was a talk from Thomas Rierink about special approaches for regridding fields between climate models and ice sheet models. I'd like to kind of take that idea and make it a little more general, and suggest that for a lot of what we do with ice sheets in global climate models, because you've got this big mismatch in spatial resolutions particularly, when we couple them, we're not just doing a regridding. We're really more doing a downscaling. And what I mean by that is that there's physics implications in how we're doing this. We're not just passing information between the two things. Or if we are, there's a whole bunch of physics that we're either implying or ignoring as we do that, whether we recognize that or not. And that's another one of these things that makes it harder to use just a general purpose coupler for some of this. The other way of approaching it is that, so we've got these different bits of physics that don't quite match between the models. So maybe what we do is we split up where that physics is. So we have maybe some of the physics that worries more about climate timescales and not so much about the spatial resolution. Maybe we can get away with sitting that bit of physics in the climate model, and then have some of the slower, smaller scale physics just in the ice sheet flow model, which is what we do. And this is actually common with a few of the other system models, in that we actually build a lot of the near surface physics from the ice sheet into the land surface model and run that along with the atmosphere on the atmosphere time steps. So that's what this little schematic is. You can see we've kind of split up our big atmosphere grid box into a bunch of statistical independent kind of snow models, each of which is doing a little bit of the ice sheet surface physics. So then what we're doing is we've kind of moved where our coupling interface is conceptually. It's no longer just between the atmosphere and the ice sheet. We've actually kind of moved it halfway, several hundred meters into the ice sheet model before we've got information that we pass. And that's helpful in some ways, and not helpful in other ways. The other issue with using these standard coupling frameworks is that the host models often aren't built to simply accept the field that's been passed. So it's all very well saying we've got a new orography field in our ice sheet model and we want to pass that to the atmosphere, and we can do that with something like OASIS perfectly well. But then what the climate model does, having been given a new orography and all the other fields in it that have to change to become consistent with that and hopefully maintain some kind of conservation, is massively complicated. And that's not something we can address with OASIS or any bit of code that sits in between these models that are written like that. So what do we actually do? It's in some ways a very simple crude system. UKESM ICE works with a file system coupling. This whole thing, the whole architecture takes advantage of the fact that UKESM, like a lot of big climate model things and things that run on big HPC, run in small chunks that are scheduled to run a month or 2 months or a year or something in a job, and then shut itself down, save its state, and then submit the next chunk to the queues. So this is a structure that actually works really well for file system coupling. We couldn't do it with a lot of other models that weren't that big and complicated. It also helps that UKESM and HadGem all run within this Silk task scheduling framework that's a very powerful general way of splitting things up into tasks with dependencies and making sure that everything runs in the right order at the right point in the system. That gives us pretty flexible control over what runs when, and the fact that occasionally everything is just stored in little files that we can go straight in and start manipulating everything we need to in a kind of simultaneous and consistent sense without worrying about what the model is kind of time stepping or running on with stuff as it goes. So yes, what actually happens? So the climate side is pretty straightforward for most of the people who are familiar with that sort of thing. We run a climate model, we accumulate a bunch of fields into diagnostics. The stuff in the ocean, although it's a 3D kind of melt field under the ice shelf, we calculate that along the surface of the ice shelf, so that's only a 2D field that you have to pass at the end of the day. We have a 3D field for the surface accumulation and melt that we have to pass to the surface of the ice sheet. And passing things in 3D, and then our target is not constant because the ice sheet surface is kind of changing in height as the run goes. So we've got a fairly complicated 3D kind of interpolation thing to do there before we can use that on the ice sheet surface. That is actually all handled within the front end of the ice sheet model itself. We use the same kind of front end that CESM does with their ice sheet. So what we pass there is a 3D field on a fixed static defined grid and bunch of vertical levels. And inside the ice sheet model itself, we worry about how that vertical stuff changes in time. The ice sheet model we're using here is Bicycles, which is an adaptive mesh model. A little bit like what Einar was just talking about. We don't have half the problems that people have with that sort of thing because we don't target the moving mesh when we couple. Bicycles has a facility built into it whereby it defines a whole bunch of regular fixed exchange grids. So we just have to couple to one of those, and then again inside the ice sheet model itself, that worries about transferring that to whatever kind of time-dependent representation of the mesh it has at the time. So that's all fine, that's all pretty normal. Ice sheet models are quite happy to accept this set of boundary conditions and then make small adjustments to them as the ice moves in terms of where things are happening for the domain. So there's a few bits and pieces to do with the moving boundaries, the ice models, as the ice sheet runs. And we accumulate stuff to hand back to the climate model, but really the main thing that we hand back is just the new ice sheet shape, how high it is, what the extent is, and the 3D profile underneath the ice shelves to hand back to the ocean. So this is now where the fun starts. All right, we don't have a very complicated bunch of stuff to hand back to the climate model, but we've got to do some pretty complicated stuff with it for the climate model to be able to run forward again. And again, working outside one of these normal coupling frameworks really helps us here. We can't do this in the coupler. We've got to make way too many adjustments to the model, to the climate models, and then building all of this natively into HadGem or Nemo, where 99% of the users really don't care about having the major complications of this sort of code to change everything about the model, because most people don't really want to run with a moving ice sheet. Having everything outside the models run in this file system sense means we can also take advantage of the sort of code that's already written for creating static boundary conditions when, say, the atmosphere model is initialized. So some of these procedures and things, we can take advantage of stuff that's already written.
Robin?
Yeah.
2 more minutes.
Cool, thank you. So it's modular. We can schedule it all into small discrete tasks, run this through this silk system. So the really complicated thing that kind of characterizes the whole problem is this ocean reinitialization. We've got this 3D topography that we have to hand back, and we've instantaneously got to change the domain of the ocean. We've got to make some volume or kill some volume. We've got to make some grid cells. We've got to kill some grid cells. We've got to do that in a way that produces a topography on the various grids that are used in the model that's consistent between those grids and that's capable for a stable flow field to exist on. So we've got to get rid of all the kind of little cul-de-sacs and one grid cell thick channels that exist in some of the grids and not on others. And then we've also got to change the flow field. We've got to change the prognostics that exist on that grid such that they are still flowing stably, even though bits of them have lost some of their volume or divergence. We do have partial cells in Nemo, so sometimes you are just resizing cells that already exist, but usually the problems really come when you just cross that threshold into when you actually have to make or destroy an entire cell. So that's all very well. There are still great limitations to what we can do. So having said all this, we can't move the land sea mask as the model runs. So we still can't really do sea level rise. We can change what the profile underneath the shelf is when we move the ocean, but we can't move where the ice shelf edge is. It's that definition between atmosphere and ocean and where that edge is that we can't change as the model runs. And there's various reasons within HadGem and within Oasis where that's a pain. The fact that we've got some of the ice sheet living in the land surface model and some of it living in the flow model makes life quite complicated in a lot of ways. So that's a problem. And some of the real problem we have is there are running in a global climate model, that there are areas that don't just need downscaling, but things that are just too small, that literally don't exist on the climate model grid when we don't have information to pass to the ice sheet. Also very practical, we prioritize getting the model running at all, ocean stability, rather than having something that runs really perfectly. So there are bits of it that are a bit chunky. The conservation is not great in a lot of places, particularly in some of these adjustments we have to make to the ocean model to keep it stable. So does it work? Yes, within these limits we've set ourselves, it works pretty well. Here's the Greenland ice sheet 1,500 years in the future, and we've retreated it a hell of a long way, and the model is still stable. I haven't really got an Antarctic ice shelf diagram I can show you collapsing nicely, but here's a run that's got an Antarctic and a Greenland ice sheet in it, both of which are evolving into the future and looking at how the sea level changes. So I've talked quite a lot about what we can't do with the model, and we've got a design that prioritizes something that works at all rather than something that's perfect. And there's a fairly small bunch of people trying to do this for us. So there are real resource issues in terms of how complex we can get, but it works. The problems that we have ultimately are science ones, and the limiting factor in most of them is the climate model. Some of it's in this small scale detail, but a lot of it is nothing to do with the coupling. It's not the coupling is amplifying biases that are there in the model. It's simply that we're working in areas of the climate model that don't work very well. There's a lot about polar climate that is not prioritized in terms of what's been done in terms of tuning and running climate models, particularly the Southern Ocean and around the shelves. So technically we can cope with it. There are scientific limitations in what we can do simply because of how well the models can work in these areas. But there is still a bunch of useful stuff we can do, even given the technical limitations and the scientific problems that we have. I'll leave it.